we're going to talk about stoichiometry. Stoichiometry is the process of using a balanced equation, and that's the big thing here. You have to have a balanced chemical equation to do this, and you can figure out how much reactant or product you're going to start with, you're going to end with when you have a reaction. So again, balanced equation is 100% necessary. Now, how you get from one thing to another in this balanced equation is called a mole ratio. And a mole ratio is basically just a fraction bar, and you use those coefficients in the balanced equation, and you put the coefficients of the thing you're leaving on the bottom, so some sort of number, the unit you're leaving, and then the coefficient value of the unit you are going to, okay? So we call this mole to mole ratio, and the units are moles here because we can use a balanced equation and the balanced coefficients with it to create relationships between everything in there. Okay, so we always have to use mole ratio if you are going from one thing to another in some sort of equation. And you have to be in moles to be able to utilize this. So here we go, we have an example here. So if you have how many moles of NH3, so you're looking for this in moles, and this is how I like to kind of organize my data. It helps me, figure out where I'm going and what I'm leaving. So I'm figuring out moles of NH3, and I'm starting with 5 moles of N2. So the good thing about writing it this way is if you see that you start here and end somewhere else, you know you're going to need a mole ratio to get there. Okay, so we're already in moles, which is nice. We put the unit and now the identifier. You have to have both at this point on the bottom, and the unit, which in this case is moles, and the identifier of what you're going to. And again, we get these values from the coefficients. So the value in front of the NH3 is a 2, the value in front of the N2 is an assumed 1, and then you can go ahead and solve. And the math is exactly the same here. You just multiply what's on top. So you would be multiplying 5 times 2, get an answer, divide by 1, which of course you can skip. And then you end with your unit and your identifier, which in this case is moles of NH3, and the value you calculate. So again, mole ratio is how we get from one thing to another in our equation. So we're going to do a whole bunch of examples here, and if you feel like you get the hang of it, you can speed forward a little bit faster to look at the answers, but it's good once you start to get the hang of it to try these on your own, and then you can check. So how many moles of H2O, so I'm trying to do moles of H2O, that's what I'm looking for. Let me go ahead and write this. Will be produced if we start with 2.5 moles of this C2H5OH. Usually I give you a little bit more room here, but that's okay. So this is what we're starting with, and it's reacted with excess O2. So right now it doesn't matter that it says excess O2. That's just telling you the thing that's going to determine how much we make is provided above, so you can just ignore that. We will, in the next video series, learn what limiting and excess is, so this will make a little bit more sense. But if it doesn't have a value right now or a number, you can just ignore it. So I'm going to go ahead always and start with what I have. You cannot start with what you're going to end with. So we're going to have moles of C2H5OH. And I want to tell you right from the beginning, you need to have moles and you need to have the identity, okay? So we're going to make sure we're doing this correct from the beginning. And then we're going to go ahead and do our mole ratio. Because we're already in moles, so we can dive right into our mole ratio. The change from this C2H5OH to what we're trying to end in, which is the H2O. And let's fill our numbers in here. So the 3 will go here, and this is an assumed 1, so we'll fix there. And then we can go ahead and easily do this math. 2.5 times 3, get an answer, divide by 1, which ends us up with 7.5. But I'm going to go ahead and make this 3 sig figs because we started with 3 here. Moles, and then you always end with the identity again. Okay, so here's our answer. So this is a pretty easy one. We're going to go ahead and try this again. So again, if you feel like you know what you're doing, go ahead and try. So we're going to do 3.5 moles of our Na. So remember, there's a lot of different Nas in this problem, but they're asking you specifically about this one because they're not giving you any other components. So it's not the NaF and it's not the NaSiF6, which we'll deal with in a second here. Okay, so we're going to go ahead and write our 3.5 moles. And we're trying to end in moles of NaF. And I like, again, writing these because you can see when it's different in a balanced equation, you have to use mole ratios. So we're going to go ahead and start with our value, 3.50 moles of our Na. moles of our Na, 2 moles of what we're going to, which is NaF. And again, use these values. The 6 will go here. E4 will go on the bottom. So again, the thing you're leaving goes on the bottom. The thing you're heading to goes on the top. Okay. And then since we're going to end in moles, we can stop right here. So the math that we can do for this one is we can take 3.50. We can then go ahead and multiply it by 6, divide it by 4, and get 3 sig fig answer of 5.25 moles. But that's not only your answer. You have to write NaF. When you change identities in stoichiometry, you have to be writing unit and identifier. All right, now we're going to go ahead and take it one step further, and I'm going to actually reference you back to this mole train station. It may have worked for you, it may not have. Either way is fine. Just a nice way to explain things. So if you're in moles, which is what you need to be in to go from one thing to another in your balanced equation, if you're in that, you can go right into the mole ratio. The issue is if you're not. If you are in grams, like you are in this problem, and you start here, before you can go to that mole ratio, you have to go to moles. So it doesn't matter if you're starting in grams, you need to go to moles, or if you're starting in atoms, you have to go to moles as well. So knowing how to convert between these components is really important, again, in this section. So let's go ahead and see what we have here. We have 10 grams of the O2, so we are starting with 10 grams. And we are trying to end up in moles of the chromium. Remember, it's saying Cr, so it's not going to pick this one. It's going to be picking this one. Okay, so I start with my grams, and then I have to use molar mass. And because there are 2 O's in our formula, we have to do 16 times 2, which is where that 32 comes from. So this is the grams of the O2 to the moles of the O2, and then you can go ahead and do the new mole ratio step that we just learned. And again, the 3 comes from the 3 in front of the H2O and the 4 in front of the chromium. So you can go ahead and try the math here. So it is 10 times 4. I like to do the whole top portion, but there are many ways to do this. Divided by 32 and then divided by 3. And I'm going to get a really small number. And remember, moles are really small, so don't be alarmed when your answers are decimals. So I'm going to go ahead and do 3 sig figs to be 417. And again, the unit is moles of Cr. Okay, let's try one from scratch here. How many grams of NH3 will be produced when 5 moles of H2 react? Okay, so I'm going to go ahead and write what I start with. So that is 5.0 moles of my H2. Now we're going to, since we are already in moles, we can go right into that mole ratio. I'm going to refer you back to this previous example. We were in grams, so we had to do a molar mass conversion before we could do the mole ratio. But because we're in moles, we can go right ahead and dive in to our mole ratio. So you have to be in moles or you have to get to moles is what I'm trying to get at. So let's go ahead and use our values. We have a 2 here. We have a 3 that's going to go on the bottom. Now, we could stop if we wanted to end in moles of NH3, which you can see right here, right? But we don't. We want to continue because we want to finish in this grams of NH3, which is why I like to write that up above, just to keep me on track. So I'm going to go ahead and do one more step. Moles of NH3 to grams of NH3. And we're just going to use the molar mass of NH3, which is 17.04. And remember, when you're doing grams to moles, just going to point this out because this is a mistake I see my students make a lot. Grams to moles is always 1 mole. Always, 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 always. The mole ratio is when you're going to be using the coefficients, okay? So you're going to be using the 1 when you're doing grams to moles, but the coefficient values are only used when you go from mole to mole, okay? So just kind of keep an eye on that because I've seen that mistake a lot. Okay, so now I'm going to go ahead, 5 times 2 times 17.04, get an answer, divide by 3. And my final answer, I'm going to go ahead and round this to 2 sig figs, is going to be 57 grams of NH3. Okay, so this is a mole to gram ratio. All right, let's take it even one step further. So how many grams of our H2, so we're looking for grams of this, will be required to produce 25 grams of NH3? So 25 grams is what I'm starting with. So again, I'm currently in grams, but to get from NH3 to H2, I have to go to moles, and then I want to finish, so I have to go back to grams. So that's kind of our plan of attack here. When in doubt in this class, in any chemistry class, go to moles. I always tell people that. When in doubt, you'll get a few points if you go to moles. So even if you had no idea what to do, you could always go to moles of NH3, and that would at least get you started. Sometimes that can jog your memory. So 1 goes with the mole. The molar mass of NH3 is something we just used, 17.04. I just added up 1 N and 3 H's for that. And then I'm going to go ahead and put on the bottom what I'm leaving. I want to get out of the NH3 and I want to go to the H2. And I'm going to go ahead and use these values here. And then again, if I wanted to stop here, I would end in moles of H2, but I want to continue and go to grams. So I need to then go back again to grams. Now, some of you may be asking, why couldn't we have just done the mole ratio if they were both grams? You can't, because moles is the only thing that is a comparable unit in chemistry. Grams is different for every element. If I did 5 grams of nitrogen and 5 grams of iron, yes, they'd be both 5 grams, but they'd be different amounts, different amount of particles, which is really what a mole is. So the only comparable unit is moles. In chemistry, grams, because of the molar mass, is different for every one of them. They are going to be different. So, in case you're wondering that. And then there are 2 H's here, so it's going to be 2.02 and 1 mole. Okay, let's go ahead and do our math here. So 25 times 3 times 2.02 divided by 17.04 and divide by 2 again. And I'm getting 3 sig figs to be 4.45. Hopefully these answers are right. If there's a mistake, let me know, but always calculate these on your own because I easily make a lot of mistakes. All right, so let's go ahead and try another one. Now, this one is, again, another example of starting with moles and ending in grams. So why don't you try this one on your own? I've been putting actually the work down below here so I can kind of just reveal it to you. So go ahead and pause the video and then work on this on your own. And if not, you can wait a second and we'll look at the work down below. Okay, so we start here with our moles of H2O. And we're trying to go to the hydrogen. Now, the big thing is students will say, what hydrogen? Whenever it's referring to something in a balanced equation, or in the problem of a balanced equation, it's going to only call it by what it's actually called in the formula. So this is hydrogen. Remember, there's 2 because it's diatomic. It's more stable in a group of 2. But when it says hydrogen, it is not referring to this or this. It is referring to the actual hydrogen molecule. Okay, so just a quick reminder about that. Then we went from mole ratio, then the mole grams, moles to grams, and then we ended up with 30, and I put a decimal point after that, 0, to make that 2 sig figs. All right, we're going to go ahead and flip this where you're starting with grams this time, and then you are going to end in moles of H2O. So again, grams of the O2, you get 15 grams, and you're going to be ending in moles of the O2. H2O, excuse me. These problems are also similar. I keep saying the wrong thing. All right, so again, go ahead and try this on your own, and then let's check out the answer. So I have 15 grams. I'm going to go ahead and do grams to moles because you cannot do a mole ratio without being in moles originally. So I went ahead and did 2 O's, which is 32 grams. Then I went ahead and did my mole ratio of my O2 to my H2O, and they're both 3s. Now you're going to say to me, do I need to show both 3s? You do. Even if they're both 1s, you need to show this step. This is you telling somebody else that you used your equation and did stoichiometry correct. So please do not be lazy. Make sure you are showing all the steps because that's how you get all the points. Even if they're 1s, they're 2s, they're all 3s, it doesn't matter. You still have to show it. And then I ended with 3 sig figs here, and since we wanted to end in moles, we could stop right here, and so we ended up with 0.469 moles of H2O. So we're just going to keep going through some examples. If you feel like you want to keep up on those, you can. If you feel like you're getting this, or you want to go ahead and try some on your own for the next few, that's also fine. Just do what you need to do. Now, again, when you're reading this problem, remember this excess oxygen is just telling you a little bit of extra information that you don't need, so don't pay attention to that at this point, although you will in the next video watch and talk about that. So how many grams of the chromium oxide we produce from 15 grams of the solid chromium? Okay, so that's a 15. It doesn't look like it, but it is. So we're going from this to this, but they're both in grams, so we need to go ahead and stop at moles in between. So our answer here, I'll let you look at the work for a moment, is 21.9 grams of our Cr2O3. Okay, so we're going to go ahead. Again, there's another example here on the next slide. Go ahead and try this one on your own. This is actually multiple choice here. So we have a balanced equation. Again, on a test, you'd probably have to predict the products and balance yourself, and then you can go ahead and use your balanced equation to do this. It's asking for grams of the tin fluoride, which is right here, and you're starting with the hydrogen fluoride. Okay, so go ahead and try that. And the answer I got was 215, so my answer I got was B. So propane, C3H8, is a gas, but we can compress it into a liquid. We are given the reaction below. This is a combustion reaction. And so we're looking for how many grams of the CO2 when we're starting with 20 grams of our propane. And a lot of times it'll just say propane, and you have to read the previous kind of story above to figure out which one that is. Now, process of elimination, you probably could have figured out what propane was, but just so you know, sometimes you do have to read the direction prior. So I got 59.9 grams of